Netcasts you love.
From people you trust.
This is Twit.
Bandwidth for Coding 101 is provided by CacheFly at CacheFly.com.
This episode of Coding 101 is brought to you by DigitalOcean. Simple and fast cloud hosting built for developers. Deploy an SSD cloud server in 55 seconds. Try it today for free. Visit DigitalOcean.com, and once you sign up, be sure to enter the promo code C101 in the billing section for a $10 credit. And by Lynda.com, the online learning platform with over 3,000 on-demand video courses to help you strengthen your business, technology, and creative skills. For a free 10-day trial, visit lynda.com/C101. That's LYNDA.com/C101. On this episode of Coding 101, we're going PWM with Arduino. Hello and welcome to Coding 101. It's the Twitch show where we let you into the wonderful world of the Code Monkey / Code Warrior. I'm Father Robert Balacer, the digital Jesuit, and joining me as always is my Super King Kamehameha co-host, Mr. Lou Maresca. He's a senior software development lead for Microsoft, and he is the heart and soul of Coding 101. Lou, so good to see you again.
Thanks for having me back.
Now, we should mention that we had to pre-record this episode because we wanted to give Lou a break. Because, Lou, you're a little busy right now. You've got some stuff going on.
Just a bit. I'm on a 24-hour clock right now, so.
Yeah, that's what happens when you have a new baby. So yes. Anyone out there who's looking at spawning a baby, that's going to happen to you.
Happens.
So
right.
Thank you for giving us this time because, I wouldn't want to do coding without you. Now, Lou, the last couple of weeks, we've had some fun. We had Smitty 2 weeks ago, and last week we showed people this. This was a little ultrasonic detector made out of an Arduino. It was an $8 device that allowed you to set parameters so you can see exactly how far away something is from the sensor. This week, we wanted to continue with that because Arduino has been one of our best topics ever. People are very interested in this. They really want to build it because it's a nice combination of hardware and software. I mean, do you find that? I mean, I've learned that some people who would be turned off by straight software development perk up whenever they can find something that they can actually touch.
Yeah, absolutely. I think anytime you get your hands dirty with something and kind of get in actually doing something, you're going to learn a lot more because you're going to run into problems and then you're going to try to fix them and you're going to find solutions for those problems and you end up learning more in that sense.
Right. We did do a project not too long ago where we controlled a very simple set of lights. This was the episode that I had with Smitty using an analog potentiometer. And what the Arduino would do is it would use its analog pin to read the value of resistance from the potentiometer, actually the amount of voltage that was making it through, and then it would set conditions based on that value. Well, that's one way to get input into an Arduino. Another way was using an ultrasonic sensor. But today, we want to play with this. This is a PWM encoder. What PWM stands for is Pulse Width Modulation. Lou, have you played with PWM at all?
Yeah, absolutely. It's a way to kind of vary your encoded. You can actually use encoded message to kind of vary the pulse signal.
Exactly. And so in broad strokes, what PWM does versus analog, while analog, let's say this is 0 volts and 5 volts, what that potentiometer would do is it would allow me to get from 0 to 5 or 5 to 0 based on where the potentiometer was held. PWM doesn't do that. What PWM is, it takes the value from the potentiometer. So it's already doing the translation from the analog potentiometer, and it encodes it into a PWM signal. And what a PWM does is every clock cycle has a low and a high. And that's when the bit is on or off.
Right.
Theoretically, it's cleaner because analog can be a little indeterminate. PWM, based on, of course, how good the encoder is, can give you a bit more accurate of a signal that propagates better over distance, which is a problem with analog. I mean, if you've ever tried controlling an analog signal from a long distance, you get a lot of fluctuation, you get a lot of discrepancy, right? I mean, that's typically what happens.
Right. Attenuation you get out of it. And then one thing with the idea here is, the signal you can have in some of these little microcontrollers is, like you said, is a high or low, 5 volts or low volt or ground. And the idea is, instead of trying to vary how high or high low it goes, it's really all you're doing is time, right? So then, and that's really easy to do when it comes to a microcontroller.
Exactly, and that's precisely what you're going to do with PWM. And that's exactly how we're going to read a PWM encoder with an Arduino. I can measure for any given clock cycle how long the signal stays high versus how long it stays low. Or conversely, if I wanted to, I could measure how long it stays low versus how long it stays high, which is essentially all PWM is. Now, like all of our other projects with Arduino, let's give you a part list really quickly. Here's 4 quick links for you to get all the pieces that we're going to be using in today's project. The first, of course, is the Arduino Uno. Now, this is one that I found. This is 361. You can find them really, really inexpensively on eBay. In fact, I just bought a set of 10 of them for $2, $2 American, like $2.21. I also bought some minis, which use the same Atmel chipset, just for some specialized projects. But I would say if you're going to start to get into Arduino, because they're so inexpensive, because you can get these for anywhere between $2 to $4, go ahead and buy yourself a set, at least 5 of them. You will not waste them, and it's much nicer than having to disassemble your projects each and every single time you're done. The second piece I would suggest is a breadboard, and a breadboard looks a little something like this. Oh, I just disconnected my Arduino. This allows you to use jumpers to make temporary connections. So instead of soldering wires, you can jump in a connection. So you could test it, see if this is the right way that you want to do it. It's also a really good way to make temporary circuits before you permanently solder something. Now, what the Arduino would cost you between $2 and $4. That set that I showed you is going to cost you, what, $750. Now, the nice thing about using a breadboard is it's kind of a universal thing. So if you start looking at schematics on the internet,
reusable.
Yeah, exactly. They're reusable. The next 2 parts are really up to you. I like this. This is a PixelStick. It's an 8 LED WS2812, and this is a RTFPixel circle. This is a 26 LED WS2812. Both of these are from Ready to Fly quads. The PixelStick is $325, and Kara, if you go to that website, yeah. So I bought a bunch of these, and then the RTFPixel circle is $10. Now, again, you can buy these much cheaper on eBay, and there's a good chance that you're going to get a decent value. The only reason why I use RTF for most of my lighting parts is because I know Paul Baxter. I have never gotten a bad part from him, and the people who have gotten bad parts from him, he's always replaced. He actually tests his stuff before he sends it out. I don't like buying what I think are cheap parts and then finding that they are broken and I can't get them replaced. So that's just me. But this is what we're going to use for today's project. In total, including this, which is a $10 Pixel ring, this project can be done for about $25. If you only went for this instead of this, you could do this project for somewhere in the vicinity of like $12. So not all that expensive. Lou, you ready to jump into this?
Absolutely.
Yeah. Before we go ahead and start the build, why don't we go ahead and take a moment to thank the first sponsor of this episode of Coding 101, and it's got to be DigitalOcean. Now, the experienced programmers out there know that DigitalOcean is the place that you go if you have a project that you want to deploy. Maybe you just want to put it out there for a couple of hours to get some real-world traffic, or maybe it's ready for global deployment. Now, the nice thing about DigitalOcean is because they use droplets, which are self-contained, nodes for you to drop onto the DigitalOcean system, you can go from that deployment for just a few hours to a global deployment with just the slide of a switch. It's really that simple. DigitalOcean is built for developers by developers, and it's used by over 400,000 of them, including me. You can deploy and configure your droplets via a streamlined control panel or a simple API, and they let you choose your OS: Ubuntu, CentOS, Debian, Fedora, CoreOS, and FreeBSD. They've got a one-click install that allows you to quickly deploy apps like Django, Docker, Drupal, LAMP, GitLab, MediaWiki, Node.js, WordPress, Ghost, Magento, OwnCloud, Ruby on Rails, and more. And all their servers are built on hex-core machines with dedicated ECC memory and RAID SSD storage. Those servers can handle up to 20 CPUs, 64 gigabytes of memory, and 640 gigabytes of SSD space each. The system is highly scalable to meet the demands of any rapidly growing application or business, and they've got auto backups and snapshots, so they take care of all that scut work in the background while you focus on building the best app or service possible. I really like the fact that they got full-feature DNS management, gigabit speeds, 99.99% uptime, and web console access with HTML5 plus SSH, SFTP, KVM, VNC for virtual desktops. But the number one feature that I love is the fact that they've got an active community. That tells me that the customers of DigitalOcean like their service. They love their service, and they're willing to come back and share their experience and their knowledge with everybody else. Folks, if you've ever looked at a service company, that's what you want. You want loyalty, and you want people who realize that they're working with a service that cares about them. It's so easy to get started that you could deploy an SSD cloud server in as little as 55 seconds. Really, you should be out of reasons not to use DigitalOcean. But if you still have, well, reservations, let me clear that away with this. They want you to try it absolutely free. DigitalOcean has incredibly affordable and straightforward pricing with servers starting at just $5 per month. And there's also hourly pricing available starting at less than a penny per hour. But we're going to make it so that you can get started today and deploy an SSD cloud server for free. Just visit DigitalOcean.com and create an account. Once you confirm your email and account information, go to the billing section and enter the promo code C101 for a free $10 credit. That's plenty to get started and explore what DigitalOcean can do for you. That's DigitalOcean.com, DigitalOcean.com. And once you sign up, enter the code C101 in the billing section for a free $10 credit. And we thank DigitalOcean for their support of Coding 101. Hey, Lou, let's get jiggy with the Arduino.
Let's get going.
All right, so I'm going to go ahead and just plug in. This is a standard Arduino Uno. If you go to the overhead shot, you can see I've got nothing plugged into this right now. This is nice and bare, which is how we want to start it, because this is how you're going to receive the Arduino when you first get it. And if you look at my screen, Kara, you're going to see that my IDE is completely blank. There's nothing on it. That would be input 11. There you go. So there's nothing in there. And what we're going to do now is we're going to take you step by step through what you have to do in order to read that PWM. We've got that little switch. We want to be able to get a value from it because we're going to be using it to control things. Remember, when we deal with Arduino, it's input, logic, output. Let's deal with the input. The first thing we have to do is we have to tell the Arduino where we're going to be receiving digital input. In this case, I'm going to be using pin number 6. What I want is an integer variable, pin 1, because I'm going to be using multiple PWM devices, so I need to reserve multiple pins, equals 6. What this will tell the Arduino is that I'm going to be giving it a digital input or digital something on pin 6. Go ahead and reserve that for me. Okay, so now let's go on to the next part. The next part is I'm going to be getting an input from that pin. I need to store it someplace. The pin 1 variable only stores the number of the pin. Now I want to store the value that pin is going to receive. So I'm going to do this, int PWM input 1. And that just creates a variable where that's going to be stored. Now, Lou, you'll notice here that I'm putting these variables at the top, which makes them global. We've both been told global variables are bad, right? Can you explain to the folks why global variables are bad?
So anything like static variables or any global variables is usually bad because you could have multiple pieces of code, especially in multi-core, multi-processes running, changing those values, and it runs into these synchronization problems. So a lot of times, if you have multi-cores doing the same thing, they're changing these values. The code would expect the value to be something specific, but it's not because somebody else changed it. So that's why it's always kind of bad to use global variables. There are some situations where you can use them, where it's acceptable, but it's not usually the only way to do it. So usually most people, what they do is they'll pass the value along to the different functions, either by reference or by value. And this way you can reference the value back somewhere else, maybe inside of a stack, rather than having it to globally declare it across all the entire application. So you kind of hand it across. It's kind of what they call a chain of responsibility. You hand that value to each function, and then it can do what it needs to do to it. And this way, everyone kind of has the reference back to the same value. Exactly.
And that's the proper way to do it. We are being extraordinarily lazy, but it is with purpose. In fact, there's a lot of the code that we're going to be giving you. This is already available on the website, so you'll be able to download it as soon as this episode goes live. Your homework will be to optimize it. There are huge sections of the code that, unlike the previous program, we left in the main program loop, and you don't want to do that. We've already told you don't want to do that. But we want to give you the opportunity to fix it. The same thing here. We're creating global variables. There's probably better ways to do it than create global variables. We can get away with it because our program is so incredibly small. But as Lou mentioned, you don't want to get in that habit. I mean, it's because Lou, I will admit to this, sometimes global variables are just too easy to pass up because it's like, I don't want to deal with passing right now. I'm just going to make this global, right?
Yeah.
And then you forget you made it global.
Yeah. I mean, sometimes you have so much data you want to pass along that you forget, I could go probably create something that encapsulates it, maybe like a structure or something, and then pass that along instead, and then it becomes just one variable you're passing along. But yeah, globals are usually easier, I guess you could say.
Just don't do it. Don't do it. All right, go back to my my screen here, Kara, because what we're going to do is we need to do a setup. So so far we've created two variables. One is storing the value of the first PWM device, the pin that it's going to be connected to. The second is a variable to store the input that we're going to be getting from that PWM device. Now in the setup, and this is how yours will look the first time you run it. I actually have a bit of OCD with the way that the curly cues work, so I'm gonna do my thing. I need them to look like this. What we have to do first is we're going to set what's called the pin mode, because the digital pins on Arduino can be input or output. In this particular case, we want it to be input, so I'm going to put pin mode, and you'll notice how the color changes. So the Arduino IDE knows that that's a reserved word. Pin 1. So in other words, I'm saying the value of 6. Pin 1 is 6. So this is 6 input. And that just tells it that pin is going to be input. Now, what I could have done is I could have just hard-coded it. I could have put pin mode 6 input. But Lou, why wouldn't I do that?
Yeah, because you want to make sure that you can pass that pin value across and make sure it's the same across all the different functions you use. So
exactly,
passing the value by itself is you're not going to always do it correctly if you do it that way.
Right. And you're going to see this several times in this program. Anytime we have a value that might be getting passed to multiple pieces of the program, it's best not to hard code it, because Lou, you know this. If you hard code something and then you change something down the line, which you will, you have to go back to all the instances where you hard coded it and take it out. This way, because it's a variable, if I change that value at the top, it changes everything, which is a better way to do it. All right, so let's go back into the setup. The other thing we want to do is we need a way to get output. And what we're going to do is our friend serial. So serial. Yep, and we love serial. Oh, CL. And again, it changes color because it knows it's a reserved word. Begin, which is going to open it up, and I'm going to set for 9600 again. Oh, 96. So now it's going to open up a serial port, set it for 9600. On this particular case, I think I'm connected on COM3. That's what the USB port gave me. All right, so let's do a super simple loop here to get this thing working. Let my OCD run its course here. And what I want to do is I need to input from that pin that I've just set up, pin 1, which is actually pin 6, some sort of value. And the command to make that happen is pulse in. It looks like this, P-U-L-S-E, capital I-N. And again, it changes colors because it knows that that's a reserved word. It's a function. And then I give it pin 1, and see, this is why I didn't hard code it, because now I can just take that variable that I called earlier, high, and that changes color, so it also knows I'm reserved. What this is doing is it's using the pulse in function on pin 1, which is actually pin 6, and it's saying, tell me how long it stays high for one cycle. Of course, this in and of itself doesn't do anything. I'm calling a function, but that's going to return a value, and right now that value has no place to go. So I'm going to go ahead and create a variable here. So what I want is to use this up top. Remember, I created this global variable, PWM input. So I'm going to put PWM input 1 is equal to pulse in pin 1 high. What that does is it means it's going to access that digital pin. It's going to listen. It's going to find out how long it stays high, and then it's going to put that value into the integer that I declared globally called PWM1, input 1.
It's basically a mini timer, hardware timer.
Exactly. That's all it is. It's saying, okay, tell me how long it stays high. I could do this. If you look back at my screen, Kara, if I wanted to, I could put low, because remember, there's two components to PWM. There's how long it stays high and how long it stays low. I could measure low instead. On this particular program, I just set it so that I measure high. But if you wanted to, you could use low. Okay, now we need to do something with that. Right now, this program would be extraordinarily boring if we uploaded it to the Arduino. It would listen, but we would have no way to know if it's actually listening. So what do you think we're going to do, Lou?
Pump it to serial.
Pump it? Yeah, we opened up that serial port for a reason. Let's go ahead and use it. Just like before, if you go back to my screen, we're going to use a function here called serial print. So serial dot print, and again, it changes colors because it knows that it's reserved. And then I'm going to give it in parentheses, PWM input 1. What this will tell it to do is it will tell it to push out this value to the serial port. And actually, what I want to do is I'm going to print line it so that it gives me a little bit of room at the bottom. Also, you've already seen this, so I'm not going to demonstrate it individually. If I just did this, the values would scroll by so ridiculously fast that you wouldn't be able to see it. So I'm going to put a delay of 200. It'll just wait 200 so that it doesn't go so crazy. So what we're going to do is we're going to go ahead and we're going to verify this. This will ask us. This will actually look through the code to see if there's anything wrong with it. If I get that at the bottom, that means okay, that's good. There wasn't. I mean, there's nothing serious in it anyway, so it should work. But we need to do something with the hardware. If you go back to my overhead shot, Kara. Right now, this doesn't have anything connected to it, so it wouldn't be able to detect anything even if we wanted it to. But we've got this. We've got this little PWM switch, this encoder, and I need to give it voltage, and then I need to use this. This is the data pin. The voltage is 5 volts. I'm going to pull it from the Arduino itself. So I've got the ground pin, and I've got the 5-volt pin, and now that has lit up, so it has power. And then this, do you remember what pin I declared for data, which was 6? So I'm going to put it into data pin 6. So now the Arduino should be able to read from this PWM encoder once I've uploaded the program. And the way I upload the program is I'm going to push this button, and then I'm going to upload. So if you go back to my computer, Kara, I'm going to push it, and I'm going to do this, upload. It's going to compile it. It's going to upload it. Done. Okay, so now this is ready to go. If you look at this, as I turn this, if I open up a serial console on the screen here, go back to my screen, Kara. This is now giving me the value of the PWM. So the PWM, the high side is going to go, it looks like it's going from 901 or so, 902, 901, all the way up to about 2099, 2100. That's about the high side. So that gives me the range. And it's gonna. This is the hard part, because this is not a really high quality PWM encoder. It's gonna vary from encoder to encoder. But this gives me a range to work with. This goes from about 900 to 2100, and I can use that range to do things. So anytime that value goes between those two ranges, I can set it to do various things. And in this case, of course, I'm going to make it trigger certain events inside my Arduino. Lou, does that make sense so far?
Absolutely, yeah. And I think one thing too you'll notice is it's kind of the sample rate too. So if you're not sampling it like you're using a loop, so the CPU is busy, it's not sampling it as fast as you could possibly sample, so you're going to get a little bit lower range of values. But yeah. Yeah. And actually, let me do one quick thing, because I know there's going to be people who are wondering why you put that delay. I'm going to remove the delay. So I've just deleted it. I'm going to go ahead and upload this again. Okay, it's uploading, and we'll see. Done uploading. Now let's go ahead and open up the serial console. And if I do this, see, it's just a mess. Yeah, so you don't want that to happen. That's why we put a delay. The delay is not really for the program, it's for me. I can't read the numbers that quickly. All right, so, but we've got a problem. We want to use this with these. And specifically, I want to use them to control the brightness of these devices. And I know the brightness value goes between 0, which is off, and 100, which is full illumination. I've got a range right now that's going to go from about 900 up to about 2100. I need to compress that down into 0 to 100 so that this gets the right values. Lou, do you remember a function that we played with that might be able to do that? So average function?
Well, no. Well, the map. We're going to remap.
Remap.
Yeah.
Got it. Sorry, I'm sorry.
We got the remap one. So going back to my screen, what I want now is I'm going to create another global variable. So int remapped. And remember, this is bad, folks. Global variables are bad. Lou says don't do it. You're a bad person if you do use global variables. So you need to clean this up. So you're going to clean this up when you get this. This is your homework. Now what I'm going to do is I'm going to use this. We've used this before to remap that range. In this particular case, I'm going to have remapped 1 is equal to a map of PWM input 1, and then between 900 and was it 2100, and I mapped that from 0 to 100. Now that's not bad, but there is an issue. Do you remember what I said about hard coding values? Not a big fan of that. I like to be able to adjust my values in one place and make sure that it adjusts everywhere else. So what I'm actually going to do is I'm going to replace the hard-coded values with variables. I'm going to have int PWM low 1, so that's the low range, equals 900. And int PWM high 1 is equal to 20, I'm going to say 2091. And actually, let me turn that to an actual, I don't know why I keep doing that. And then here I can change this from 900 to PWM low 1, and I can change that from 2100 to PWM high 1. And the advantage of this, of course, is if I reuse these variables, which I will, because I'm going to be doing this in several loops, I now only need to change it here. If I have to calibrate my device, I change it there, and I will be able to affect everything. The other thing I want to do is I want to see both the original value and the remapped value. So I'm going to change my serial console command. What I want is I'm going to print this one. That's going to the original value. Then I'm going to get serial print.
Fine.
And then I'm going to do this. And what this does is it gives me a tab. So it's going to tab it for me. And then serial print line. And this will be remapped. There we go. And I'm going to add the delay. Oops. There we go. So what this should do now is it should allow me to see both the original value of the PWM and the remapped value. So let's upload this. Of course, there may be an error, but let's find out. Give me an error. Did I screw something up? Oh, wow, I got it right. Huh, go figure. That's never happened before. All right, it's done uploading, so I'm going to go ahead and open up a serial console again. And now what you see is that's the original PWM input on the left-hand side, and on the right, that's the remap value. So it goes all the way up to 100, and on the bottom, it goes down to 0. So I've just turned it from a range that the lights can't use to a range that the lights can use. This is actually, does C# have something like this, Lou? How would you do that in C#?
So you'd probably have to do, I don't think it has a actually built-in function for it. So you'd actually have to take the range and do a little math to say, hey, you know, this is really just half value. So let's say 900 to 2100 is, you know, obviously instead of 200, it's 1. You need to get it on 100, so you cut it in half, and then you map. Then that will map the ranges in. So
right, yeah. This is not something tremendously complicated. This is just math. But one of the nice things is that math is built into the Arduino library. If you go back to my computer carrier, you'll notice there are no includes here. I did not include any additional libraries. So all of that math on all those functions are actually part of the original Arduino IDE, which I actually kind of like. So folks, now what we have is we have a way to input a value using this PWM and into the Arduino to remap it so it goes between 0 and 100, which is the brightness that we want for our LEDs, and then do something with it. So what I'm going to do now is I'm going to go ahead and bring in this string of LEDs. This is an 8 LED string of WS2812 pixels. This is little LEDs. The other thing I'm going to do is I don't have many more power plugs for my Arduino here. So instead, I'm going to use these little jumpers to bring out. So here's my ground, and I'm going to put my ground over here. And here's my 5 volts. I'm going to put my 5 volts over here. And now I can power a bunch of different devices by going through the breadboard rather than going through the Arduino. That's all this is. These are straight through, so that's like a piece of metal under each one. So in this particular case, I'm going to put negative here and positive over here. And as you can see, it lights that up again, so we're good to go. I also want to give power to my, my Pixel, so I'm going to give it positive and negative. But of course, my Arduino does not yet have a way to address the LEDs, which is something that we are going to change right now. I'm going to take this and I'm going to put it into data pin 7. And remember that, because I'm going to have to tell the Arduino where to find that. Let's go ahead and open up a second sketch here, which looks like this. So this, I've already, of course, I've done a little work here. You've seen this. If you've watched the previous episodes of our Arduino work, you know the fast LED library. This is a library that gives us control over WS2812 lights, among others. There are a couple of other pieces here that you need to know. Define the number of LEDs. This tells me, or this allows me to tell the Arduino when it's dealing with the library, the fast LED library, how many LEDs it will be addressing. I'm telling it 8. It will also allow me to tell it what data pin is the LED connected to, and it's connected to data pin 7. This will create an array called LEDs, that is the size of the number of LEDs. In other words, I'm creating an array exactly the size of the number of LEDs I have. The reason why I'm doing that is because I can fill that array with values, and then those values, which will do things like brightness and color, get pushed down the line to fill it out. Now this is what we just did. We have our pin 1 is equal to 6, our PWM input is equal to 1, our remapped is equal to 1. I've added this to the setup. These two pieces you've seen before. This piece is from a previous assignment. This is the initialization for the fast LED library. Now the loop looks just like it did before. The difference is I've added all of this. This is a loop that vacillates the array between blue and red. See, so what I've done is this is hard-coded. LED 1, 2, 3, 4, 5, 6, or 0, 1, 2, 3, 4, 5, 6, 7 is blue. Then LED 0 through 7 is red. So it should go red, blue, red, blue, red, blue. But you'll notice something that's a little bit different. Here, in set brightness, normally I would put a value. But instead of a value, a hard-coded value, I am putting the variable remapped 1, which we just created to go between 0 and 100, depending on what that PWM is doing. So Lou, what do you think it's going to do when we upload this?
So in between each sample, each loop, you're sampling the brightness again, so it'll change the brightness LED as before it blinks or blue or red.
Exactly. And then it will allow me to say how bright this thing is going to blink. So let's go ahead, it's compiling. When I compiled this sketch, because I'm using the fast LED library, it's actually going to take quite a bit of time. It's got to go through that entire library, look at all the code, figure out what it needs, and then it's going to incorporate that into the finished binary that it uploads. It's now uploading, and now it is done uploading. Now if you go over to this shot, the overhead camera, what you'll see is I've got the LEDs, and as I do this, I can make them, actually bring down the lights. Bring down the lights, there we go. So I can make them super dim or super bright. That PWM input is allowing me to control how bright the LEDs become. In fact, at this point, it's just blotting out the cameras. You don't get the full effect on the cameras because the cameras aren't great at picking up the full range of brightness. But what we have now is we have a good way for us to take a remapped PWM value and turn it into the brightness of our LEDs. And in fact, if we look at the serial console here, just like before, I get my remap values. So that's between 0%, so that's off, or 100%, and that's full brightness. There we go. That's actually pretty simple, is it not?
Yeah, very simple.
Very simple. But, Lou, we don't want to stop there. You know what we should do? We should control something else. I like that. We've got one PWM device right now. What I want to do is I actually want to have multiple PWM devices. I've got two switches here. See, I've got the second one. and I want to tie this in, and I want to have it control something else about the LEDs. I'm already controlling brightness. You know what else would be nice to control? If you go to the overhead, Kara, this is a set value. So how fast this thing is blinking, that's just set by the delay. Remember I showed you how the delay allows me to delay between the loops? Well, what if I set that for a PWM value, a remapped PWM value, so that I could control with just one of these encoders how fast the loops run? I can, and let me show you the code to do it. Let's go and look at the code. So if you look at the code, everything looks the same as it did in the last instance, except for this. I have now added a second pin. Pin 2 is equal to 5. So I now have the LEDs being controlled by 7, and I have pins 6 and 5 getting input from 2 PWM devices. I've also added 2 more global variables. And again, Lou, what did we say about global variables?
Don't do it.
Don't do it. So you're going to have to figure out how to do this without using a global variable. And there is a way. Again, we're just being lazy. In this particular case, to make it easy, I'm using the same naming convention. So I know if it says PWM input, it's what I get in. I know if it says remap, it's what I remap. It's just the difference is 1 and 2. I have also added, I have to add pin mode for the second one here. So pin mode, pin mode, pin 2, input. And just like it did for the first one, that will set that pin so that it is ready to receive data from my PWM device. Now in the loop, you've also noticed that I don't want to hard code. So these are already preset values here because I kind of cheated and I did this beforehand. But I've calibrated these for these particular encoders. Now you'll notice these encoders are both the same, but look at the low range and the high range. One goes from 900 to 2099. The other goes from 1015 to 2010. That's just what you're going to get when you buy cheap components, folks. They don't always work properly. And then the rest of it is the same. It's just the strip of LEDs, but you'll notice that the delay has been changed. It's no longer a hard-coded number. It's now the remapped number from PWM input number 2. Lou, does that make sense?
Absolutely.
Yeah, and you will notice here. So we did the remapping function here, remap 2, and instead of going from 0 to 100, I go from 0 to 500, and that's because I just wanted more of a range for the delay. I could go to 1,000, but that would be a ridiculously long delay, and I didn't want to do that. So go back to the overhead. We have to do the same thing with this encoder that we did with the last one. Actually, let's unplug this so I don't blow anything up. I need to give it power. So in this particular case, purple is negative, and gray is positive. And the only reason why it's like that is because I ran out of black and red. White is my digital pin, so I'm going to plug that into number 5. So now I have 2 PWM encoders here ready to do their thing. I'm going to go ahead and plug myself back in. Okay, and hit the button and upload my code. And if you go back to my screen, you're going to see, again, it has to go through the fast LED library. It's compiling the code, and as soon as it's done, it's going to go ahead and upload it. Lou, this is actually, for me, this is one of the most satisfying things about working with Arduino. I like working out problems in my head with software, but to see it pushed to
instant feedback, yeah.
It's just, it's nice. Okay, and now it's uploading and done. Okay, so now it's uploaded. If you go to the overhead, Kara, so I've got, just like before, if you, lower the lights, this one controls the brightness. I can go from no brightness to high brightness. Sorry for anyone out there who's having a seizure right now. But this encoder now allows me to slow the delay. So as I turn this PWM encoder, it's increasing the delay at the end of each one of those loops. So I can go from this, which actually almost looks like the same color, to that. And that's a delay of 500.
Very cool.
And if I look at the serial console, this is why we put this in here. This is for debugging. My monitor now has that. So I've got 2 columns. I've got, let's speed this up. There we go. We've got 2 columns. So I've got the original PWM1 on the leftmost side, then the remapped, then the original PWM2 on the next column, and then the remapped. So as I get to this, it should get closer and closer to 500.
There you go.
There we go. Almost there. Boom. All right, so go ahead and come back out. and go ahead and bring the lights up and come wide again. So this is a super basic example. And if you're worried about the hardware, don't worry, because we are going to be covering this on know-how. But the cool thing about this is I could have multiple devices. I've got several digital pins on my Arduino. So if I wanted to control everything from what arrays it was using to the types of loops that it was doing, I could use different PWM devices in order to make it work. One more thing, and this is the real reason why I'm using PWM. PWM is used by remote control models. So I can use a receiver like this to control PWM features on my Arduino with a basic off-the-shelf transmitter, which we're going to be doing in just a bit. But first, let's go ahead and thank the second sponsor of this episode of Coding 101. Hey, Lou, have you ever heard of Lynda?
No, absolutely.
No, I haven't. Exactly. Yeah, we love Lynda because Lynda is our repository for knowledge on the internet. It doesn't matter what you want to learn. Do you want to learn job skills so you can maybe pad out your resume for the next time you go for that big position? Well, you can do that at Lynda. Do you just want to learn some skills for office work, Excel and Word and PowerPoint? You could do that at Lynda. Do you want to learn more about a hobby? Perhaps you want to improve your photography skills, figure out how to film from a drone, or just learn a new programming language. Well, lynda.com lets you do all of that and more. Now, lynda.com is for the problem solvers. It's for the curious. It's for the people who want to make things happen. Maybe you want to develop that next generation app. Maybe you do want to take those photos. Maybe you do want to sharpen those HTML skills. It really doesn't matter what you want to do. Lynda will let you do it. Now, new Lynda courses that I can recommend right now are Node.js Essential Training, Programming iOS 9 and Gameplay Kit, Up and Running with COBOL, and Programming for Non-Programmers, iOS 9 and Swift. Lynda makes it easy for people of all experience levels to find the right information. Not patronizing information that's too easy or really advanced information that's too hard, but something that fits the way that you learn. What I really like about lynda.com is they customize their learning experience around you. You get to learn at your pace, the way you want to learn, with experts who actually do this for a living with really good production value. So you don't have to worry about bad audio, bad video, or bad lighting messing up that knowledge coming into your knowledge hole. I tell you folks, lynda.com is probably one of the most important things, the most important resources you will ever have. You do get to watch and learn from those top experts who are passionate about teaching, and that passion comes through in the videos. You do get to browse course transcripts, so you can jump to a specific part in a video that answers the questions that you're having rather than having to watch an entire course in order to find maybe that one thing that you forgot about Adobe Premiere Pro. You get to download tutorials and watch them on the go, on your Android, your iOS device. You can stop and start again on your Mac, your PC, your laptop, your desktop. They want to make you learn the way you want to learn, and I think lynda.com is above the rest in that manner. Of course, you can create and save playlists if you want to share with your friends, because one of the best ways to learn, and this is a super secret, is to get your friends involved. If they're involved in what you do, you're going to like it more. Your lynda.com membership gives you unlimited access to training on hundreds of topics, all for one low flat rate. Whether you're looking to become an expert, you're passionate about a hobby, or you just want to learn something new, I want you to visit lynda.com/C101 and sign up for your free 10-day trial. That's lynda.com, lynda.com/C101. And we thank lynda.com for their support of Coding 101. Hey, Lou. I think maybe we need to bump this up a notch. What do you think?
Absolutely. So do some microcontroller, remote controller stuff.
Let's do some remote control stuff. But first, yeah. I want to up my LED game. This is not bad. This go to the overhead. This 8 LED strip. That's fun. But I'm thinking let's maybe go a little bit of this. This circular ring. I've actually been really liking it the last couple of days. So let me unplug this. You don't have to, but I'm being nice today. Let's take off this 8 LED strip because, well, now we're disappointed in it. And we're going to go ahead and connect this to our breadboard. And again, this is why we want the breadboard. The breadboard makes it so easy for us to rewire our circuits on the fly. So this is my positive. This is my negative 5 volts. And this is all being powered off of the Arduino, which I would not suggest for a long-term project. Ideally, you would want to get an independent 5-volt power supply just to offload from the voltage converters. And then I will plug this into pin 7. Now, here's a funny thing. Because I set this board to think it only had 8 LEDs. When I reconnect this, this is what it will look like. If you go ahead and drop the lights a little bit. It is only contacting the first 8 LEDs in the ring. If you go back to my computer, Kara, you'll notice that's why this is important. Remember, this is the number of LEDs. The number of LEDs tells the Arduino how many LEDs it's going to address, and then it also creates an array of 8 cells. So it's only pushing out enough data for those 8 cells. If you remember, when Smitty described how WS2812 LEDs worked, they take their bytes off the stack and then they pass them on. Well, if the Arduino is only sending out enough bytes for 8 LEDs, all of the rest of the LEDs get no data. But if you go to the overhead, the rest of the functions here are working just fine. So this is working just like it did when we were using the other strip. I can control brightness and I can control delay. But let's go ahead and change it so that we actually have access to everything. Now, here is a completed program, and this is the one that you're going to be able to download. This is completely commented. All the show notes that you need are in here. This will tell you exactly what each individual piece does. First thing you'll notice is I changed the number of LEDs from 8 to 7. This has all the rest of the code that you've already seen. PWM input, the PWM remapping. I did change this. You will notice that instead of hard coding a bunch of arrays, I now used a bunch of for loops. So for loops will allow me to do the same thing that I did while hard coding the array, but instead of having to specify what each and every single array cell would be filled with, this fills it for me on the go. Lou, loops, you use them for arrays, right? I mean, because hard coding is ridiculous, especially when you start getting up to 26 LEDs.
Absolutely.
Yeah. So let's see what this does. So if I upload this, and it's going to take a while. There we go.
So you could have, like you said, you could have just mapped all 26 values,
right?
You know, in line if you wanted to. But in this case, you're making it a little more simple and just using a loop.
Right. And while that goes ahead and compiles, I'll show you something else that we had to do. There's an issue here. Tell me about interrupts, Lou. What do interrupts allow us to do in software?
Well, essentially what they do is they're hardware based, and what they can do is they're kind of work off of a value that if something triggers an interrupt, then the actual microcontroller will stop what it's doing at that point in time and go and fire the interrupt code. And so the key here is it's kind of hardware driven, and it's more efficient than doing stuff in loops because it's again, it's hardware driven. So it allows you to go and do stuff kind of asynchronously, and so it's not really synchronous. So it'll happen at any point in time, and it can run that code at any point in time. And most microcontrollers will support this. Actually, pretty much any CPU will support this. And so, like I said, it's a little bit more efficient than just doing a loop and sticking things on the stack.
Right, which is what we did. So we just did a loop and we stuck it in the stack. And the reason why we did this, we could have done, see all this PWM input for 1 and 2 and the remapping for 1 and 2. We could have put it at the beginning of the program loop. The problem with doing it that way is then it would only read, it would only interrupt its process to read from those digital pins once all of the program in the loop was finished and it went back to the top. Right. If that loop takes an inordinate amount of time, it could be a while before you could readjust your settings, and we didn't want that. So what I did was I did it incredibly inefficiently. And those of you who download and upload this code to your Arduinos right out of the box, you're going to notice that at times it lags. It's because I really am kind of stretching what this Arduino can do. Because each and every single time, every single one of these for loops fills a cell. So that's every single LED. It has to stop. It has to look at the PWM input for number 1 and number 2. It has to remap it, and then it puts that into the brightness and delay for that particular cell. That is incredibly inefficient. So what we want is we want you to make it more efficient. All right, so this finished uploading. Kara, if you go ahead and go to the overhead shot, this is what it looks like. Now this side controls brightness just like before, but what this one does is this allows me to control my speed. So this is incredibly slow. So this is just LED by LED by LED, and then if I turn it all the way around, it does this little animation for me. What I like about this is it's actually very simple. This is just a couple of for loops. And what I'd love to see you out there do is to take this and animate it the way you want. What I was thinking is you can set it so that you'll have like one bright LED followed by slowly tapering LEDs in brightness. So it looks like a fire ring that just goes around and around and around. And again, these are things that you can control with these PWM encoders. And if you go back to my screen, you'll see that the serial monitor looks just like it did for the past code example. So this is just taking in the PWM values, it's remapping them, and then it's pushing it out. The one difference is that I now have some sort of animation on my LED rings. Go ahead and bring the lights up, Kara. But we've been limited by one thing. We've been limited by these. Like, I mean, I don't really feel like being tied to this. It's not a bad thing to do, but wouldn't it be cool if I could control everything remotely? Now, this is a super low-cost transmitter. We've been using this on Know-How for some of our drone projects. It's kind of been replaced, but I've repurposed it to now control PWM devices that are connected to an Arduino. What I'm going to do here is I'm going to remove these PWM devices. Remember, one of the reasons why I use this is because it's a standard. I can pull it out from here, and I'm going to plug it straight in here on channel 5. And I'm going to pull this one out. And I'm going to push it in to channel 6. Now, the cool thing about these kinds of receivers is that they can receive power through these same cables. So this is actually being powered. The power is coming from the Arduino. Again, I wouldn't do that. Normally, I'd want to use an independent 5-volt supply, but in this particular case, I will make an exception. If you look at my code, I did have to, where's that? I did have to recalibrate, and this is why we have the debug. The high and the low numbers are actually much closer than those other two PWM encoders, again, because it's a more expensive device. I get more constant values. But I need to set those because I need to calibrate what the highest point and the lowest point is on this transmitter. So let me go ahead and turn it on, turn off all my switches, set those for Mead, plug this in, and now we're going to go ahead and upload the new code. So all I did, the only difference between this code and the previous code is that this has been remapped for the values of this receiver. And as soon as it's done, it's compiling it right now. It's going to start the upload in just a tiny little bit, hopefully. Maybe if it finishes going on, I don't know. It's gonna compile the script. Lou, talk to me while this. Oh, there we go. Okay, now it's starting to upload. And we are done. So go ahead and drop the lights a little bit, Kara. If you go to the overhead. Here we go. And I am nowhere near the device. In fact, I'm gonna back over here. But with the controls on my transmitter, I have full control over the delay and full control over the brightness. Oh, imagine doing that for a light show at your house.
How much more efficient is that RF controller compared to the little PWs?
Oh, I looked at the current draw. Like one of those little PWM encoders pulls 5 times as much power as that RF receiver. So it's not efficient at all. Those are not. The primary advantage of these is these are 45 cents each. So I got in fact, when I needed an analog potentiometer, I just pulled it off of this because that was cheaper than buying an actual potentiometer. So go figure. And see, the nice thing about this is I'm doing this as a simple sort of holiday type episode where I can control lights. And remember, I just showed you I was able to move from 8 LEDs up to 26 LEDs by changing a single value. You could go to Home Depot right now and buy a string of 500 WS2812 lights, hook it up the exact same way. You'd have to give it its own power supply because that's way more power than an Arduino can supply. But you just change the value from 26 lights to 500 lights, and you could control everything. I mean, isn't that cool, Lou?
Very cool. Super cool.
I love this. This is a lot of fun. And actually, the other thing I wanted to do is because I have 6 channels on this receiver, I could use the other channels, for example, to trigger a different a different animation. Like let's say I wanted to do sort of a clock face, or let's say I had an array instead of a ring. I could trigger that. The other thing, and you gave me this idea beforehand, right now I am wasting so many clock cycles because I am doing a digital pin read twice and a remap twice every single time one of these LEDs gets its value. You were saying maybe set one of the switches to be my interrupt. So if I hit the interrupt, then it waits for values. Right. Otherwise, it just goes, right? I mean,
or another option, you use a timer too, which is very similar to an external interrupt too.
Yeah. And so those are all things that hopefully that you can take and complete on your own. Lou, any final thoughts on this? I mean, I know I want to send you a couple of these because you know, it's Christmas, and hopefully you can play with it in your copious free time when you're not dealing with baby. But anything else you think people should keep in the back of their mind as they're starting to get crazy with Arduinos?
I would say that just continue to play with it and learn about, you know, like you're doing, is you're addressing things and you're changing things, you're variable and you're changing the variance and stuff like that. And of course, like you said, try to make more efficient. So I would, you know, you're going to find that as you tweak things, you're going to mess up and you need to go back and figure out what you did wrong. And as long as you're using things, you know, dump like in the serial port or in the serial console, you'll be able to see kind of what's happening. And so just use that as a learning bed for you to kind of figure out what's going on and what's not working, what is working. And then, like you said, variable change things, add more things, take things away, add more controlling capability. You know, like, I don't know, you can add, you know, something that will variable the LEDs based off of how bright the sun is or something like that, right? So you can do more things with what you're actually giving to the viewers.
Right. And I want to build on something that you said. I would make sure you always put in a function for a serial console debug. I mean, as advanced as you might get your project, nothing comes in handier than a quick way to dump values out to the serial console so you can plug in and see, well, what's happening? You know, what values am I getting? Suddenly everything is not working. Let me see what the raw data looks like. That's one of those things that a lot of people forget because it's easy to forget once you start hooking up screens or you know, advanced sensors to this. But give yourself an easy way to find out what's happening inside the program, and it's always a good thing.
It's kind of like the old school way of debugging. And in fact, some companies today actually do it by pushing things what they call telemetry endpoints now, and they can figure out what programs are doing at any point in time just by looking at the data from the telemetry endpoint. It's the same thing as they're just pumping data to a quote-unquote virtual console, and they're looking at what the data looks like, and hopefully it's the correct data, so to speak.
Absolutely. Folks, you can find all of these notes. The libraries that we used, the actual source code is available right now in the Dropbox. It will be linked inside the show notes. You can download it, and as long as you have the same parts that we have, you could recreate this exactly as you've seen on this episode. Of course, we want you to take it home, and we want you to improve it. Get rid of those global variables. Break out the program loop so that it has individual functions. Show me a better way to do interrupts. This is part of what it means to move from being a code monkey to being a code warrior. When you stop copying code and you start actually creating code of your own. Lou, this is a special episode for us because this is actually the last episode of Coding 101.
Yeah, sad.
It is sad, but at the same time, it's not. This is actually a good thing because what we've realized over the last 2 years of doing Coding 101 is a lot of these projects kind of deserve to be in know-how. And you may have noticed if you listened to the announcement last week, know-how will be moving to 2 episodes a week, and actually perhaps even more if the audience continues to grow. So coding episodes, coding projects like this are going to end up in know-how. And of course, Lou, I'm going to invite you back every time we have one of those. Also, Lou, I believe you're becoming one of our regular rotating co-hosts for This Week in Enterprise Tech.
Yeah, I'm super excited about that.
Yeah, exactly. So we're going to be keeping Lou. We're going to be keeping the family together. We're just changing the Twit schedule because as Twit grows and as we get new shows like the second episode of Know-How or the new Screensavers, both of which did not exist before we had Coding 101, we've learned that there's some programming that we could probably let go. Like for example, Before You Buy is now part of Know-How, MacBreak Weekly, iOS Today, and the new Screensavers. And of course, we're going to try to keep all the talent, but we want to give you the best programming possible. And in that sense, I think Coding 101 has done its job. I do want to say thank you. Thank you to absolutely everyone who let us do this. I mean, working at Twit, being part of the Twit family, this is just fun. It's just fun. I come to work each and every single day, and I love the fact that I get to broadcast. I love the fact that I get to play with things like Arduinos, like .NET, like PHP, like everything we do on Know-How or This Week in Enterprise Tech. And I get to do it with fantastic co-hosts like Lou Maresca. And I only can do that because you all keep tuning in each and every single week. And so I hope you continue to do that. In that sense, this is not the end of Coding 101. This is just the sending off of Coding 101 into something newer and better. Personal thanks to everyone who made this show possible. I want to reach back, of course, to Lisa and Leo, who they were really the ones who wanted a coding show, and so we created Coding 101. Of course, to Snubs, who was my first co-host on the show, and I miss her greatly. I loved working with her. And of course, when she left, I got Lou Maresca, which was sort of a dream come true. Lou was someone who we had very early on in my Twit career on This Week in Enterprise Tech, and we brought him in for Coding 101 because he was a good fit. So it's been a wild ride, and none of it would have happened without you. Lou, could you please say goodbye to the audience who has come to know you as the expert, the code warrior, the guy who always has the answers.
Absolutely, yeah. And like I said, I want to reiterate is I just appreciate the opportunity to kind of be able to give you that the kind of the 101 look, the ivory tower look of many different languages, many different opportunities to have you learn and get into coding. And like you said, moving into the more practical sense, practical application now, that's where know-how is at. And getting your hands dirty is really going to kind of get you bootstrapped into learning different languages and learning different ways of doing things and actually applying that programming knowledge, right? So I think this is a great start opportunity. You can always go back and review all of the different episodes we did and then apply that to, different ways of doing it in hardware and other projects. And I think that that's going to be an invaluable thing. And I also want to thank you, Padre, for giving me the opportunity to kind of come and work with you, because you're an amazing guy. And it's actually, I've learned a lot myself. So, I mean, it's not just me trying to teach things. I've actually learned a lot myself. And again, thank you to Leo and Lisa and Twit for giving me the opportunity as well.
Folks, that about does it for this episode of Coding 101, this last episode of Coding 101. It is a happy time. It is a joyous time. We are so happy for what is coming in the future. But we do close this chapter. And as we do, I'm Father Robert Balacer. This is my Super King Kamehameha co-host, Lou Maresca. And Lou, one last time, how do we end our shows?
End of line.